that do miss. All right, we're going to dig in looking at normal distributions today. Just a little recall for you. Random variables are either discrete or continuous. In Chapter 5, we looked at discrete variables and their distributions. So remember, discrete variables, they have outcomes we can actually count. So we could count how many heads we flipped on our coin. We could count how many sixes we rolled. I can count the number of students in this class. So when we had those distributions, we did graph them a little bit, and they looked just basically like a little histogram. They were easy for us to plot, all the outcomes we could count. Now we're going to start digging into our continuous variables. Remember, continuous variables, they can assume values between two given values. You're thinking, wait, Miss Guy, whoa, what does that mean again? So it means if you were to measure my height, let's say, and let's say whatever device you were using only measured in inches, you would measure me at 67 inches. Well, I might really only be 66.5 inches, or maybe I'm really 67.5 inches. So my height could be anywhere in between 66.5 inches up to 67.5 inches, anywhere in that range. Continuous variables typically deal with measurement because you're limited by your measuring device. So again, measuring in inches versus being able to go out to the half inch or hundredth of an inch, things like that. So my height could be any of those range of values. When we're working with continuous variables, instead of having the distributions look more like this histogram bar graph type deal, they're going to be curves. They're going to be bell-shaped curves. So a normal distribution curve, we're going to use it to study many variables that are approximately normally distributed. Really, Miss Galley, well, what does it mean to be approximately normally distributed? It means that you're going to have a continuous, a symmetric, bell-shaped distribution. So you're thinking, well, wait, what does that look like? I'm just going to draw a little sketch. We're going to see a bunch of these today. So the curve will look something like that. We're going to see a few different examples today. So continuous means there's not going to be any gaps, there's not going to be any holes. Symmetric means if I fold that in half, the two sides are going to match. And bell-shaped, well, it looks kind of like a bell. If you want to, you could kind of draw in. I'm not the best drawer in the world, so bear with me. So you can kind of make it look like a little bell. So that's what our curves are going to look like for our variables this time, okay? I know I'm not the greatest artist in the world. Now, to actually get the curve, I know right now you're looking at this equation, some are like, ooh, I got to get it down, it's an equation, it's a formula. Please don't. Please don't waste your pencil lead on it. I just want to make you aware that this is the formula used to actually create the curve. Are we actually going to do the plugging and chugging and create the curve? No. We're going to use the curves that are given to us. But I just want to make you aware that these curves aren't just coming out of thin air. There is math behind it, okay? Now, part of this formula, though, we're using the mean, we're using the standard deviation, there's the variance popping in there. So for each distribution, the curve's going to look a little different. Because each distribution, you're going to have a different mean, different standard deviation, and things like that. So the shape and position of your curve are going to depend on the mean and the standard deviation, like we saw in the formula. So just take a look at all the different, and these are just a few different curves. There's so many different shapes. Some are skinnier, some are wider, some are positioned more on the left of the x-axis, some are positioned more to the right. They're all continuous though. There's no holes or gaps. They're all symmetric. I can fold them in half and the sides match. And they're all bell-shaped. Again, some are skinnier, some are wider. So now, some more of the properties. These properties will be on your test. I guarantee it. I will ask you to give me the properties. So you have two choices today. Option 1, write them today in class. Option 2, they are found on page 314 in a blue box in your textbook. So it's up to you. I will give you time today. If you want to jot them down as we go through them, that's absolutely fine. You can have them in your notes. Or when you go to do some practice questions that might ask you about the properties, or you go to prepare for your test, study for your test, If you just want to go to page 314, you can. So completely up to you. Or also, if for some reason I go ahead of you right now, you can find these on page 314. And there's really not any different ways to word these, so they pretty much are what you see on 314. The first property we've talked about, it's bell-shaped. I even drew you that fantastic picture of a bell. If you want to draw your own, you sure can. The mean, median, and mode, they're all equal, and they're all located at the center of the distribution. The distribution's unimodal, which means it just has one mode. The prefix uni means one. We have one mode. It's symmetrical about the mean. The mean's at the middle of the distribution. So that'd be the place where I'd fold my graph in half, so the two sides would match up. It's continuous. That's one of the properties we've already talked about. So it's just one nice smooth curve. There's no holes, there's no gaps. And some of the curves that we saw pictured earlier, none of the curves ever touch the x-axis, and they never will. They'll get really close towards the tail end on either side, but they're never going to touch the x-axis. Total area under the curve is equal to 1 or 100%. And then property number 8, guys, this is just the empirical rule that we worked with in our first unit. It just tells us the area under the curve, or what percent of our data values will fall within one standard deviation of the mean. So within one standard deviation of the mean, we're at 68% of our data values. So if we take our mean and we add one standard deviation, and we take our mean and subtract one standard deviation, 68% of our data values should fall in that range. We do the same thing for 2 standard deviations, and about 98% of our data values will fall in that range. And then within 3 standard deviations, about 99.7%. So the same percents we saw in our very first unit. The empirical rule, property number 8, just a little more visual for you guys is all. Again, I wouldn't take the time to really draw out the curve, but just to make it more visual of what we're looking at when we're saying within one standard deviation, your mean is at the middle of your distribution. Within one standard deviation means I add one standard deviation to the mean, I subtract one from the mean, and then in there, in between that range of values is where 68%, roughly 68% of our data values should fall. So that's the idea. If it says within one standard deviation, we're adding one to the mean and subtracting one. Same for 2, same for 3. Okay? So now the issue is, and I showed you guys earlier just some pictures of different normal distribution curves. And all the normal distribution curves, they depended on the mean and the standard deviation for your distribution. Well, the issue is that means we'd have to use that ugly formula I showed you for every different data set we have. Statisticians are like, hey, this kind of sucks. I don't want to have to do this for everyone. So can't we come up with a way that we can make something uniform for every variable that's normally distributed? And they came up with the standard normal distribution. So the standard normal distribution will work. We can apply this curve to any variable that is considered to be normally distributed. It will work. The normal distribution, the standard normal distribution, is a normal distribution and has a mean of 0 and a standard deviation of 1. Mean of 0 and a standard deviation of 1. So the formula, same with the last one. I just want you to be aware of it. I'm not going to have you use it. I'm not going to have you actually draw out the curve. But I just want you to be aware of where this curve comes from. I don't want us, we're going to be using this curve quite a bit, and I don't want you to be like, well, we draw this curve and who knows where it comes from. There is a formula that's used to give us the y values so we know the specific height of the curve for each specific, in this case, they're going to be called z values, and I'll talk about those in just a second. But again, just something to make you aware of how we actually get the curve. Now, if you have a normally distributed variable, you're thinking, Ms. Galley, so how can we get all those different curves just onto one? How does that work? So in order to make it work, we take our variables and we change them into standard normally distributed variables by finding what are called z-values. The z-value or z-score that we find is how many standard deviations our value is away from the mean. So your z-value or z-score, you would hear it referred to both ways, is how many standard deviations whatever value we're dealing with is away from the mean. Now, just for today, while we're getting used to this, we're not going to do any changing from a normally distributed variable to a standard normally distributed variable. We're not going to find the z-values today. We're going to do that tomorrow. Today we're going to be just given the z-values and we're going to work on using those to actually find the different areas. So today is kind of the basics we need to then do the application piece tomorrow. So bear with me. There's not going to be any specific application today. We've got to get the basics down before we can apply, and we will do that tomorrow. Now, the nice thing is for us, all the nitty-gritty calculations have been done for us, finding all the different areas for any z-value from negative 3.49 to 3.49. So what I would probably jot down here is just that we're going to use Table E. It's going to give us the areas, and you're going to know that. You have to write down the rest because when you open to Table E, you're going to know it's labeled with what you're dealing with. So Table E is going to give us all the areas we need. All the calculations have been done for us for any z-value from negative 3.49 up to positive 3.49. It's all there. It's all done for us. So let's try this out, but I do want to lay out for you just a little step by step. Take it or leave it if you like. We are going to do some examples. You always start by drawing the curve, just a sketch of the curve, showing the z-values or z-coordinates that you are specifically interested in, and then you're going to shade the area that you're interested in. If you draw the picture, it makes life so much easier. It does. So again, it's up to you if you want to write down the step-by-step, you can. We're going to do some examples. Find the appropriate figure. Now this piece right here, there is a procedure table on these pages in your textbook. So if you're jotting these steps down, I would just jot down that there's a procedure table on page 316 to 317 that can be helpful if you're having trouble with finding the areas. There's going to be times when we add areas, there's going to be times when we subtract areas, we're going to use one in there, here and there. So if you need just some help initially getting started, that procedure table does a nice job of really outlining things for you. And we're going to go through examples today, absolutely. But if you need a fallback, that page is there for you. You're going to use Table E in Appendix A. We talked about that earlier already. And then your final answer. I don't care if you give me a decimal or a percent. Now, if the question actually asks you what percent of people or what percent of cars or what percent of light bulbs, then I would expect your answer to specifically be a percent. But if you're not asked specifically for a percent, Doesn't matter to me which way you write your answer. Completely your choice. Alright guys, so let's try this out. Don't know why that box is hanging out there, I apologize. Find the area to the left of, and we have z equals negative 2.12. Now if you're thinking, wait Miss Guys, so how do I know where to put negative 2.12? Well, one of our properties said the mean is 0, and it's at the middle of our distribution. So we know the middle is 0. So negative 2.12, is that going to be to the left or to the right? It's going to be to the left. Now, the exact placement of it, I'm just going to take a little flip back here. The exact placement of it, if your z value were right around negative 2, so it's going to be roughly right around there on the curve. Now, your sketches, guys, they don't have to be perfect. They're just going to help us find the areas. So I'm never going to grade your sketch. The sketch is just helping us get the areas is all that's happening. So negative 2 is roughly around there. It's not a huge deal if it's not in a perfect spot. It's not a big deal. And we want the area to the left, so we're going to shade the area to the left. So this is all I meant by drawing the picture. Draw your curve, just that bell-shaped. Put 0 at the middle. Find your z value. Again, rough sketch. And then shade whichever direction you need. If it says left, if it says right, and we'll even get into it where we do between two z values. So now we're going to use the table E. It's on page 788 in your textbook. If you want to flip to that, I will also have it up here. And our z value was negative 2.12. So how do you use this table? Our z values are in the left column. Negative z values are on the left part of the table. Positive z values are on the right part. So I want negative 2.1 and then I want a 2. Everything to the nearest tenth is going to be in the left column. And then whatever you need for the hundredths is across that top row. So my hundredths place is a 2. So if I put these two together, I get my negative 2.12 that I want. So I follow this row over, and I follow this column down. And so I get 0.0170 as my area. Again, I know, guys, we're removed from the application piece right now today, but we need to focus on finding the areas before we can apply this, before we can touch any application. And I know that's tough, but that's what we need to do. All right, so the area to the left, 0.0170. And that's the answer. That's all to that question. The next one, it says find the area to the right. 0's at the middle. So 1.75, a positive z value, is going to go to the right. Roughly somewhere in here. Again, it doesn't have to be perfect. And we want the area to the right. So here we go. There's my picture. Now, I know you're thinking, wait, but Miss Golly, the areas in the table, we just found one to the left, and that was the area in the table. And you're right. All the areas you're given in the table are to the left of the z value. So you're thinking, so now what do? I want an area to the right. Well, so let's use what the table gives us. Let's go ahead, try it out. Look up the area for 1.75 in your table. Let's take a little pause here. Let's make sure you can do that. I have it jotted down up here. See if you can get it. If you can't, please raise your hand. I'll come around and help you out. So the table gives us the area to the left. So I know that this area over here is 0.9599. I don't want that though. I want the other piece. So how am I going to get that red shaded piece that's to the right? Subtract it from 1. The area under the whole entire curve equals 1. So if I know this piece over here to the left, the blue piece and the red piece together are going to equal 1. So let's do a 1 minus. And what'd you guys get? 0.0401. So that's our area. So if you want the area to the left of a z-value, you look it up in the table, write it down, rock on. You want the area to the right of a z-value, you're going to have to look up the area in the table and subtract it from 1. So if you want to jot any little side notes down on any of these examples, please do so. Our next task is going to be to find the area between two z-values.